Hi everybody, welcome to another video in differential equations, section 3.6, 3.7. I combine these two sections together because these two sections deal with numerical methods, pretty much programming, so I combine them together. Right. So we first section 3.6, we take a closer look at Euler algorithm. So this is back in chapter 1 when we study about the Euler method when we solve the differential equation. Right, now we take a look at the problem. The problem here is a linear first order differential equation with initial condition. So initial value problem, we have derivative equal to a function of x and y. Now, if we let phi of x be the actual solution, and we have y of x naught equal to y naught is the initial condition. Of course, then phi of x naught is equal to y naught. We need to estimate y1, y2, and so on. Right. Now, integrate the initial value problem from x naught, from xn to xn plus 1. So integrate from xn to xn plus 1 on both equations. On the right hand side here we have a definite integral. And since this is a solution, we can put that back in phi of x is the solution. You can put it back in that. So both sides will be a definite integral. So fundamental theorem of calculus on the left hand side. Fundamental theorem of calculus, let me write this out. So that is fundamental theorem of calculus. I'm looking at the left hand side here, where f, a capital F, is any antiderivative of f. So since we have derivative here, the one without derivative is an antiderivative. So we have antiderivative evaluated that point minus this. So pretty much exactly what we have for the fundamental theorem of calculus. Now the rest of the problem is what do we do with the integral on the right hand side? Well, on the right hand side, this we can estimate using by the way, we just move this to the other side, and that's what we have. Now if we look at the integral here, there's a lot of different ways to estimate the integral. Back in calculus 2, we have the midpoint rule, the trapezoid rule, and the Simpson rule, and then a lot more higher order estimate for the integral. So if we can estimate this, we will have the formula to get to find a xn plus 1. So that is if we know x naught, y naught. So the point of this is if we have x naught, y naught initial problem, we start x naught, and then we can go to x1. We can calculate x1, and then we can estimate y1. So we go from y1 to y naught. In here, what we have is we go from phi of x sub n to phi of xn plus 1. And then so with this, this is the recursion relation. You see that if we put 0 in here, we go from 0 to 1. We go from x0 to x1. If we put 1 in here, we go to x1 to x2, and so on. So we have the initial condition, and then inductively or recursively, we can go to x1, y1, and of course when we have that, we can go to x2, y2, and then we just keep doing that. So the problem is just how well we can estimate that integral. Then we can just recursively evaluate this. Right. Now, the way we estimate the previous solution is this. So now we estimate the integral using x of n plus 1 minus x of n is a function of x and phi of xn. So I'll try to draw this out and we'll see what is the estimation will look like. So we just want to estimate the integral from xn to xn plus 1. And the function, let's say, hold like this. That is the solution. Right. So we estimate the integral from x of n to xn plus 1, and we know that the definite integral is the area under the curve, right? So pretty much we estimate this area under the curve from xn to xn plus 1. So we try, so this integral on the left hand side, we'll calculate the area under the curve. Now, area under the curve, we can, the easiest one we use here is we use xn plus 1 minus xn. Pretty much xn minus xn plus 1 minus x of n is going to be this. And then we have the values of the function at xn and phi of xn. So we talk about this. Let's use this. So this is values of the function. It's going to be that. So instead of calculate the area under the curve, what we multiply, what we have on the right hand side is this area is the rectangle. So this is like the Riemann sum. Go back in Cal 1, we use rectangles to estimate the area under the curve, and in this one, yes, we use that rectangle to estimate the area under the curve. Right. So that area of that rectangle is approximately equal to the area under the curve, therefore approximately equal to the integral. Now, of course, you say that is not a very good approximation, right? And of course, it is not. So the better way is, instead of doing this, we should use like a trapezoid instead. So we could do that, and that area of the trapezoid is the better approximation. And that's what we have for the improved Euler method. So rather than use rectangle estimate area under the curve, we use the trapezoid. The trapezoid is the area of this is 1/2. I mean, I will draw the area of the trapezoid. The height here is A and B. The area of the trapezoid is equal to 1/2 h A plus B. So pretty much we have 1/2 of the width times the sum of the bases, this and that. So in this case, the estimate, the integral is equal to 1/2 the width, the function at xn, the function at xn plus 1. So that is the area of the trapezoid. This is a better approximation. And put that together, we have the new Euler method. The new and improved Euler method is this. So we start from this y, and then we go to add the area under the curve, estimate as the area of a trapezoid. So this is the formula for the area of the trapezoid. Right, so let's look at the first example and see how it works. Improve Euler method. So this is going to be the improve Euler method. So I'll solve the initial value problem using the improve Euler method. Initial values is, the equation is y derivative of y equal to y naught is equal to 1, and estimate the solution using h equal to 1, h equal to 10 to negative 1, 10 to negative 2, and 10 to negative 3. And if you forgot, the h is the distance between consecutive points. So h is the difference between consecutive sample points. Right. So we have like x0, x1, x2, and so on. Right. So now, and of course, by the way, this, if we solve it, it is easy. The solution is e to the x, because e to the x is the only function that has the derivative equal to itself, right? E to the x derivative of e to the x is equal to e to the x, and of course e to the 0 power is equal to 1. So the solution is the obvious one, e to the x. But we're not focused on how the solution here. We focus how do we use the improved Euler method. So improved Euler method, one way we do this is we make a program and we run it. Another way, if the solution is kind of simple like this, we might write the solution explicitly. So this is the solution that I have typed before we have here. So the point here, because we have h is different of consecutive sample point of x. So initially we start with x0, and then we go to x1, x2, on the way to xn. And the distance between consecutive x values is h. So on. So that's what we have. Now, I will do this problem in two different ways. The first one is called I call this is the forward. The second example, I do it in the backward. Same problem though, but I do in the backward direction. So now, let's say if we have the solution, we have initial condition x0, y0 is equal to 1. So initially, that's where we start with x0 and y0. Now, y1 is equal to y0 plus h over 2, y0 plus y0 plus h y0. So why is that? So let me write the solution, the improved Euler method. Let me write that correctly. Right. Yeah, so pretty much that. Now if I put 0 in for n, I will have y1 equal to y0 plus h over 2 f x0 y0 plus f x0 plus h y0 plus f of x0 y0. Right. So that's what we have, right? Improve Euler method. Now let n equal to 0. We have that. Now how do we end up to this? The function here is y. So since this is the equation, we can say that the function on the right hand side is equal to y. So in this case, f of x0 y0 is just the second component y0, and f of x0 for the function here will be just the second component. and I forgot an h here, right? So then an h here. Right, so we write this, we have h over 2 y naught plus y naught. Now h f of x naught y naught, the function is just the second component. So that's why I have y1 is equal to this y naught plus h over 2 y naught plus y naught plus h y naught. Now multiply this out, we have y naught, we have y naught plus another y naught, make it 2, multiply this, we have h y naught and h2 y naught. Factor it out, we have this, and finally, since y naught is equal to 1, I will substitute into here and I end up with that. So y1 is equal to this, right? Now the same thing, by same thing I mean we have y1 equal to this. Now we increase the n by 1, so the 1 becomes 2, so you can say y2 is equal to y1 plus h over 2 y1 plus y1 plus hy1. You can do the same thing, and then we multiply it out, we have y1 plus hy1 plus 1/2 h squared y1, and because we can factor it out y1, and we have this. And then since y1, this is y1, if we substitute into y1, we have that times it, going to be square, and recursively we're going to have y sub n is equal to that, to the n power. And finally, since we do this, x sub n is going to be start from x naught plus n times h. So from x naught to xn, there will be n of those h in the middle, and so we substitute this, x naught in for 0 and xn equal to 1. Substitute, we have n is equal to 1 over h, and substitute in that, so we have y1 approximately equal to this. So that is the solution when we say the going forward. From x naught, y naught, we can generate x1, y1. From x1, y1, we go to x2, y2, and then so on and so on. Essentially, we have that. Now this is going forward. Now let's go backward. Going backward, I will start from the Euler method itself. Try to write small because we may not have enough space. So I write this one again, very small. So this solution kind of, let's say, backward. So y sub n plus 1 equal to y sub n plus h over 2 f of xn y n f of xn plus h. You know what, I'm not going to fit in one line, but just continue. Yn plus h f of xn yn so I'm just going to write that. Now what we know is f of xy is equal to y. By the way, you have to do one like this in the homework room. Put another book so I get closer to the camera. Now, so the function y is the function xy is it's just going to be the second component. So we write this. I have y sub n plus 1 equal to y sub n plus h over 2. Now, f of xn, yn will be just the second component, so that will be just y sub n. So this is just this, because the function is just the second component. Right, next we have the function. Once again, is just the second component, so I'm just going to say y sub n plus h f of x n y n. Once again, the function will be just the second component. Y sub n plus y sub n, make that 2. Combine like terms here. Combine like terms there. And then the function is just the second component, right? So this is just y sub n. Right, let's multiply it out. 2 and 2 cancel out, we have h y sub n. Multiplies out 1 half h squared y sub n. And factor out y sub n, we have 1 plus h plus 1 half h squared y sub n. So that's what we have. Now, if we do that recursively, we can go back and we can write, let's say if we want to go down one step, that's what we call this one backward. Instead of n plus 1, now if we reduce the index by 1, now instead of n plus 1, we have n. And these index are reduced by 1. And we just keep doing that. And we can substitute this into here. Think about that, right? And then y sub n, reduce the index by 1. That's what we have. Now, since this is equal to y sub n, we will substitute all of this into y sub n. And we just keep doing that, keep reducing, and all the way down to y0 is equal to 1. So we just do y sub n and then y sub n minus 1. In fact, let me just do that. And now we have y sub n minus 1 equal to 1 plus h plus 1 half h squared. Now reduce in index by 1. And that is y sub n minus 1. And we substitute this into y sub n minus 1. So bottom line is we will have y to n plus 1 equal to 1 plus h plus 1 half h squared. And then we just have another 1 plus h plus 1 half h squared. We just multiply this back into y0, which is 1. And the key here is how many of this do we have? So think about this. We start with n plus 1. Go to n, there's 1. Just count pretty much. N plus 1, there will be 1. Right? If we go from n plus 1, let me write like this. N plus 1 to n, there is 1. N plus 1 to n minus 1, 2. N plus 1 to n minus 2 divided by 3. So what if we go from n plus 1 to n minus n, which is, why not, what will be this number? right? So originally from y sub n plus 1 to this, if we have yn plus 1, if we substitute this into y sub n, we're going to have 1 plus h plus 1 over 2h square times yn minus 1. So you might think about this. X sub n plus 1, I mean n plus 1 back to n, there's 1, back to n minus 1, there's 2, all the way back to 0. How many we have here? So you can write this like 0, right? So we can pretty much we count from 0 to n. From 0 to n there will be n plus 1 numbers. So this number is going to be n plus 1. So think about that. Go from n plus 1 all the way back to 0. How many do we have? And in that case we have n plus 1. So y sub n plus 1 is equal to 1 plus h plus 1 half h squared to the n plus 1. Of course, if we reduce back to y sub n, we're going to have just n here. Meaning, if we reduce the index, we just have y sub n equal to 1 plus h plus 1 half h squared to the n power. Bottom line is we're going to have that. So whether we do it backward or forward, that's what we should have the same thing. Right? So we substitute y sub n into here, we will have 2 factor of this to the yn minus 1. So from n minus 1 back to n, there's 1 power. N minus 1 back to n minus 1, there's 2. N plus 1 back to n minus 2, there will be 3. And when we go to n plus 1 back to n, there will be n plus 1 power. So that's just counting pretty much. So we have the solution is like this. So I'm going to type that in the calculator. Instead of h, I'm going to type x instead. X squared divided by 2 go to the power of 1 over x. Right, so I type that, and let's say in this case, estimate the solution. Estimate the solution when h is equal to 1, 10 to negative 1, 10 to negative 2, and 10 to negative 3. So that's easy. And enter the function. And then if I want to estimate, I will hit y variables function y1. And then if I have h equal to 1, I have 2.5. So I'm going to write this here. If h equal to 1, y is equal to 2.5. Now if h is equal to 10 to negative 1, y equal to. Alternatively, if you don't want to hit variable, y variable, and y1 like that, you can just hit alpha zoom. I'm sorry, if the bottom menu pop up, you hit alpha trace. That's y1. And we evaluate at 10 to negative 1, meaning 0.1. Meaning the smaller step, we should have the better approximation. So that would be 2.714. Now at h equal to 10 to negative 2, y equal to. So that's just 0.01. (2.71823). And then of course h equal to 10 to negative 2 is the same thing, right? Of course we know the solution is e to the x. When e to the first power is equal to that, as you see, when h, the step gets smaller and smaller, the distance between consecutive x gets smaller and smaller, the more step we have, the better solution. So this one approach to the actual solution. So that's the point. Of course, if we want to find the error, we say when h equal to 1, we can just take that, subtract the numbers. So we will take e second division, subtract. So when h equal to 1, the error is that when h equal to 0.1, so the step between the x gets smaller. We take e minus that number, because e is the actual solution, so the error is 0.0042, and h equal to 0.02. We take e minus that number, e minus this number, and of course that is very small number. So the smaller the step between the x, the better solution we have, and that's the way it should be. So you have one homework problem like this, where you have to deduce the formula for y sub n, something like this, and the way it works is in the homework it derive the formula backward. Of course, we can check the solution forward like that as well. Right. Now let's actually go to the programming part of the section. So improve Euler method. So we're going to put this. So for the initial value problem, so this is our problem. That is our problem. We said n is the number of steps. So in that case, the width is equal to xn minus x naught divided by n. So pretty much we go from x naught to xn, and we divide into a bunch of steps, and there are n of them. So the width is equal to xn minus x naught over n. So this is the width, and we have x naught, x equal to x naught, and y equal to y naught. That's what we initialization. So this is where we start with. So instead of compute, this should be initialize. So we're going to do that. Those are constant, and then we enter into a loop. So we start from 1, we calculate this, which is capital F, and we calculate this, which is a capital G, and then y is equal to y plus h over 2 f plus g, and x of course is equal to x now, I mean the previous one plus 1. Of course, when we write like this is not really a way. Of course, when we say x equal to x plus h, and then you said that is wrong, but this is not the way we think in the computer programming. In computer programming, we should write that with the column, meaning we're going to we calculate this, and whatever it is, we're going to make that equal to f. Calculate this, whatever it is, make that equal to. So in this case, we will let x equal to x plus h. So we know they are not equal, obviously, but we're going to let the new x values equal to that. So in programming, that's how we write it. I mean, it's not math, but okay. Now, in the TI-83, TI-84, actually, we're going to program using a calculator. So we enter, this is the program, how it goes. Of course, the function, this is not actually the way we write it, but depends on the problem. We will write a function, depends on what we have. By the way, it turned out to be very nice, even though it takes some time to type all of that, but you will see that it turned out to be very nice. Alright, so let's look at the problem. Use the improved Euler method to estimate y's up to for the initial value problem. So this is our problem. With n is equal to 10, find and plot the estimate solution y sub x. Right. So in this case, the program that I use here, C, is going to be the terminal values. Terminal value, I mean, for that I mean xn. Meaning that we talk about x capital N. Right. Now let's rewrite this program first before we type in the calculator. So the program will be prompt x, y, c, and n. So meaning initially we will have to say what is x, what is y, what is the terminal values, and how many steps do we want. In this case 10. Right. Next we type exactly. This is how it works in the calculator. When you type the program, you see. So we calculate this and we store into H. Next, we have the for loop. When we write like this, we mean the index, we go from 1 to n, increase by 1 every time. So we go from I. So when we do this, meaning that we have I equal to 1, 2, 3, all the way to n. And you just keep doing for every single n. So this is called the n, the for loop. Sorry. Next, the function at x and y. Since the function is x plus 2y, here we just say x plus 2y, we store into f. And next, the function that x plus h and y of h of f. So we will have x plus h. So the function is the first plus the second. So I'm just going to say x plus h. That is x. And then plus 2 times this will be y plus hf. And we store that into G. And finally, so this step depends on the function. This function, this time the function is the first one plus 2 times the second one. So this depends on function. So that's the step we have. And then next we will have x plus h stored to x and y equal to that. So the next step is the updating step. X plus h stored to x, y plus h over 2 times f plus g stored to y, and then we'll do the end loop. So this step is updating, the update step. So after this, we will have the new x. Like if we have an original x0, y0, when we do this, we have x1, y1, and then so on. Now, what I did not write here is we can actually store the answer into one list, so we can plot the answer at the end. So this is new that I did not put in the program, part of the program, but we can say we can store x into the first list. The first list and the shell of I. So if the first I equal to 1, we store that in the first element of the list. If I equal to 2, store in the second component of the list. and then we store y into list 2 of I. When we do that, we can end the program. Right, so that's how we have a program. Right, how do we program on a TI calculator? By the way, the reason I use the TI because I'm not sure what programming language you're using, but I think the TI is the simple one. Later on we'll use Excel also, something that's more accessible. Right, so you see the program here, obviously that's what we use. We hit that and we will create a new program. So go to new program and then create new. By the way, you have to do one problem like this in the homework, so make sure you know how to write this. Right, let's say Euler, so E, where's U? Right, alpha, because in this way it will type the numeric, the alphabet values. If you want 2, we have to hit alpha 2, sorry, alpha 2. Come on. Let's try that again. So the program is, I just do that, alpha E, alpha U, and then 2, Euler 2. Okay. So that is the name of the program. So again, when we hit program, new, and then we enter the name, and then when we hit enter, that's where we have the program. So this is the program now, right? So when we hit enter, it automatically go to edit. So this is where we enter the program. Let's look like that. So first prompt. By the way, don't worry, all the for and the prompt and the end, everything is under the program key. There's only a few functions. So program, is there prompt there? Nope. Okay, input and output, there's a prompt. So it will prompt the value of x, comma, y. Bear with me, it will be a while. C and N. Right. First step is calculate the step. So the terminal values minus initial values divided by how many steps do we have, alpha, and store into H. Right. So that now we store, now we write the loop program. This is the for loop. The for loop will run for index I that equal to 1 to n, and it is increased by 1 every time. If we hit 2, it will be 1, 3, 5, 7, but it is 1, so it will be 1, 2, 3, and so on. Close that. Now within this loop, first we have x plus 2y store into f, and then x, this is the function x plus 2y, so that's why we enter x plus 2y. If the function differently, choose different function. Where was that? Okay, x plus h. Yeah, the problem is we don't have the keyboard, so we have to type one at a time, so I can't. Y plus alpha h alpha f, and we store this into G. Right. Next, update x plus h store into x. Update the y. Y plus h over 2 as far as computer program goes, I think this is one of the simplest form of programming. So we have that, and we store into y. Because the memory of this calculator is not much compared to a computer, so the language is very simple. And then we store x into list 1, so second number 1, and we store that into the cell I. So if I is 1, that will store into the first component of the list, and y is 2, the second component of list, and so on. Y we store into list 2 of I. And finally n. Program as you see, there not much we have. We only have like more than we have, but we only have like a few functions. Okay, where are we? Program, edit. Okay, we need to end that, to end the loop. That's it. That is the first program in the calculator. Now it's ready to run. So from here we can say that first of all, it's be safe if we clear a list. So hit stat and edit. We don't see any. Oh, we see something here. We better clear that. To clear a list, highlight the list and hit clear. Do not never hit the delete key here. Just hit clear, highlight the list, hit clear, and enter. If you hit delete, it's going to be, if you actually hit delete, then you actually delete the list. In that case, just delete everything and have to enter it again, like L1, and enter the names here, second 2 for L2. If you actually delete the list, you have to enter all the names again. Once again, just delete everything and enter the new name, L1, L2, L3. Of course, if you need more, then just type more. Right, so the bottom is L1, L2, there will be nothing below that, so the list will be blank. Right, now it's ready to run. Hit program, execute. So when you create, it's new, and then we edit when you want to execute the program. Hit program and execute that program. Right, X. In this case, initially X naught is equal to 0, Y naught is equal to 0.25, and the terminal values C is equal to 2, and we use N is equal to 10. So those are the values that we enter here. So we start with 0, Y naught 0.25, C is 2, and then we do N of them. Right? Done. Okay, how do we know if the answer is correct? Hit stat, edit. Now we have the X values and the Y values. And the question is, what is Y of 2? So here we write, after we run the program, Y of 2 is equal to 23.961. Right. So we have L1 and L2. Now, how about plotting those solutions? Well, we do that. Above the Y equal to the stat plot. Very important that we hit the second stat plot, and number 1, hit enter. We're going to turn it on, and X is going to be L1, Y is going to be L2, and we're going to do the scatter plot. Right, so just turn it on. sorry. Those are the plot of the solution. By the way, since y2 is equal to that, so let's change the windows. Hit Windows, it only goes from 0 to 2, right? So I would say, how about negative 0.1 to 2.1, and increment is 0.1 each. The y value is from negative 1. Let's go from 23 something to make it up to like 30. And each increment is about 5. So those are the solution. We can plot the solution. Of course, if we want more points, we can plot more points. So it's very nice, right? Now, it will be even better. It will be even better if we actually have a solution and we plot the solution, the actual solution compared to this. So I'm going to solve for the actual solution first. It's not part of the problem, but I'm just going to solve for it. And then when we compare to the actual solution, you can see that the approximation is turned out to be very good. Right. So this is the program. And when we graph, that's what we have. Right. Very important. When we're done with this, we have to hit start plot and have to turn off. If it's not off, and it will mess up your graph. Only turn it on when we have something on the list and something we want to graph the list. Otherwise, it will mess up your computer, your calculator. Right now, I'll keep it on for a moment. Right. Now to solve this, I'm going to do this quickly because this is not the focus of the section. So y naught equal to x plus 2y, and y of naught equal to 0.25. Right, I'm going to solve this rather quickly. Move the 2y over because this is the linear first order equation. Right. And so this is standard form linear first order equation, integrating factor. And we have negative 2. So to do that, we have e to the negative 2x. So that is integrating factor. I will multiply on both sides. Right, so I multiply that on both sides. The left hand side is going to be a product rule. The right hand side is going to be that. That means we have to do integration by parts for that. So to get rid of the derivative, we integrate right. Integration by parts. Right. In this particular, we let u equal to x and v equal to e to negative 2x. In that case, derivative du is equal to dx, and dv, sorry, dv is that, so u dv. Right, so v is integral of that is negative 1/2 e to negative 2x. Right, and substitute into the integration by parts formula. uv minus v du. Right, so that so this equal to negative 1/2 x e to negative 2x, negative, that's plus. Right, integrate that, we have negative 1/2 x e to negative 2x. Integral of this is plus 1/2. Integral of e to negative 2x is negative 1/2 e to negative 2x plus c. And we write this, we have negative 1/2 x e to negative 2x minus 1/4 e to negative 2x plus c. The left hand side is equal to this, so I will write that again. Right, since we want to solve for y, we divide both sides by e to negative 2x. So y equal to negative 1/2 x, that cancel out, minus 1/4, that cancel out, and I move this to the top, turn to positive. Right, so that is the solution. And then we have the initial condition, y not equal to 0.25. Y of 0 equal to 0.25, sorry. So put 0 for x, make that equal to 0.25. Negative 1/2 times 0 minus 1/4 plus c e to 2 times x is 0. E to 0 power is 1. So I have 0.25 equal to, this is negative 0.5 times 0, which is 0. And minus 1/4, so on the left hand side this is negative 0.25, and that's c times 1. So we solve for c, c is 0.5. Right, like I said, this is not the focus of the section, so that's why I do this rather quickly. Put it back there and we have the solution. Negative 0.5x minus 0.25 plus 0.5 e to the 2x. Right. All I want is to get to the solution. Now we can enter into the function y equal to negative 0.5 x minus 0.25 plus 0.5 e to the 2x. Now hit enter. So that the little square is the estimate solution and the curve is the actual solution. As you see, it looks very close to the actual solution. So I said it is very nice when this all come together. So that was we'll make this program and store into the list, and of course there will be a lot of things. But first thing when to do is now let's try this again with more points. All right. So before we do anything, hit start, edit, make sure we clear the list, highlight the list, hit enter, highlight the list, hit clear and enter. Now of course we can do more points if we need to. Program, and we run that. Now we start, x naught is 0, y naught is 0.25, c it end at 2, and let's this time say we take 20 points, 20 steps. And then when we graph, we're going to have more points, but the solution is very close. So the more points we have, the better solution we have. Of course, it turned out to be very nice. Right. So perhaps when you go to engineering or computer science, you never have to program anything in the TI calculator, but at least I want to show you that. So this is set. I said as far as programming language goes, it cannot get any simpler than this kind of language. It's pretty much straightforward. Yeah. Especially the higher and higher level of programming right now, it will get very complicated when you actually want to just program the simple things. Right. With that, we go to section 3.7. Right. We briefly go through this because this requires calculus 3, and some of you did not take calculus 3, and like that will be a little bit unfair if I ask you this. By the way, whatever in this video, section 3.6 and 3.7 will not be on the test, because if you have to enter the program like what we did there, even though it's nice and all, I really want it, but it takes a lot of time to do it, so we're not doing it. So the idea here is the Euler method. We use the f of x naught, f of xn, yn, which is the first derivative. It will be better if we use more the higher derivative. Of course, as we see the power series or the Taylor series, the higher order of derivative we have, the better approximation. The more terms we have, the better approximation. So let's say if we estimate using the second derivative, and things get more complicated where we say the derivative is the function of x and y, but in reality y is a function of x itself. So it's only derivative with respect to x. So when we check the second derivative, we end up with this. So I'm just going to put this in the note. If you want to, we can check that. And then we estimate, instead of using the first order Taylor series, we use the second order Taylor series, and we have a sample. And the example of that is we do here. So I just put this example so you can see. Like I said, this requires a very good understanding of calculus 3, which, like I said, it is not a requirement for the course, so I cannot expect you to do that. And this is kind of difficult problem regardless. Right, what we do now instead is another method of estimate the solution. So the Taylor method is where we use the higher order of derivative. The Runga Kuta method, instead we use higher order derivative. We use many points. So when we go from x, let's say x0 to x1, this method, we take the midpoint of that, so we use more points, and with that it will improve the calculation. Right. So the derive of this method, once again, is outside the scope of what we're doing here, so we're not going to do that. So this is the second order. The most popular one is the fourth order Runga Kuta method. Right. So in this case, the x is updated by that, the y is updated by that, and we're going to do all of this to get k1, k2, k3, all of the case. Right. We're going to do the same problem as the previous section, but this time we use Excel. Before we do Excel, just make sure that the calculation works. We're going to do this by hand. We're going to have this. And then the function in this case is x plus 2y. We're just going to do this by hand. So whenever we put in Excel, the calculation can check with what we have in Excel. Right. Now, initially we have x0. So x0 is equal to 0. Y0 is equal to 0.25. That's where we start with. And n equal to 10. So what is h? H equal to, we end at 2, so be 2, start 0, divide by 10 step. So that is 0.2. So h is 0.2. Right. So that's what we have, and then we will calculate. We calculate K1 to K4, and then update the K. Right. K1. F of xn, yn, so it is x naught, y naught, which is, the function is the first one plus 2 times the second one. If we do that, we have 0 plus 2 times 0.25. That is 0.5. Just do that by hand. K2. Of course, I can type this on the calculator too, but it takes too much time. So I'm just going to do it by hand, and then I put on Excel, will be better of use of time. K2 is going to be this. So the function of x naught plus h over 2 y naught plus h over 2 times K1. The function x naught is 0 plus h over 2, 0.1, y naught 0.5 plus h over 2, 0.1, y naught 0.25, h over 2, 0.1 times K1, 0.5. And the function say the first one plus 2 times the second one, 0.25 plus 0.1 times 0.5, 0.1, 0.25 plus 0.1 times 0.5. That's 0.3. So 0.1 plus 0.6, 0.7. K3. K3 is f of x naught plus h over 2 y naught h over 2 K2. So it's f 0 plus 0.1 y naught 0.25 plus h over 2 0.1 plus K2 is 0.7. So 0.1 plus 2 times, pretty much is that, but K2 is 0.7. And 0.1 plus 2 times 0.32, 0.74. K4 x naught plus h y naught plus h K3. F of 0 plus 0.2, 0.25 plus 0.1 is, h is 0.2, sorry. times K3 0.74. So we have 0.2 plus 2 times 0.25 plus 0.2 times 0.74. 0.398. Right. And 2 times, 0.2 plus 2 times that, 0.996. And finally, the update step. X0 is that plus, so X2 is, X1 is easy. Now, and Y1 is equal to Y0 plus 1, 6 will be 1 on each side and 2 in the middle. So we do that. 0.25, that is Y0 plus 1 divided by 6 times 0.5 plus 2 times 0.7 plus 2 times 0.74 plus 0.996. And we have 0.9794. This just to confirm with what we're going to enter in the Excel. It might be wrong. We'll go back and check it later, but keep that back pocket. Now let's open Excel. Right, I'm going to enter here. Just zoom this in a little. Right. First of all, I would enter right here H. .2, not messing with that. And here we will have xn, yn, and then all the k, and then the new simple enough. Much faster if we use Excel than the calculator. Right, initially we start with 0 and 0.25. Right, K1. K1 is the function of xn and yn, and the function is the first one plus 2 times the second. So we will say this cell is equal to this one plus 2 times this one. Sorry, wrong one. Right, so that's 0.5. That's good there. The next one, K2, is that. Will be equal to x sub n, which is that one, plus h divided by 2. So this divided by 2. or you can say 0.5 times h1. But you're not going to enter h1 like that, because when we move the columns, the h is still there. We do not shift, we do not calculate anything down the column here. We're going to fix that entry. So to want to fix that entry in Excel, we're going to put the $sign there and the $sign. So we're going to, regardless of when we copy the formula down, the h is always that cell. So that is the first one. So x plus h divided by 2, and then plus 2 times y naught, which is this guy. I mean this one. Plus 2, sorry, plus what? H over 2, so 0.5 times that cell again, but so that's 0.5 h times k1. Close, and we have 0.7, which is good there. Next, equal to k3 will be x sub n plus 0.5 times h. Once again, we have to fix the shell, plus that plus 0.5 times that cell, but it is fixed. And we're missing something, so this is x, and then this is y, and then 2 times y. Y is not okay. Oh, we did not multiply by k2, right? So 0.74, so we're good so far. And then k4 is that equal to x naught plus this cell, but once again we have to fix the cell, plus 2 times y naught plus h, this one, but it is fixed, times k3. Oh, I know where the mistake is. And I have 0.996, which is good. By the way, in the formula, let me put the Excel away just for 1 second. In the formula, I forgot that it has an h here. It has an h here, so I forgot to put an h here. So just have to multiply by 0.2. Right, so I have the answer as 0.3959. Okay. Now back to Excel. Let me check. Oh, so that's good. H1 is fixed. H1 is fixed. H1 fixed. finally y update the y will be, we start with this equal to that one plus 1 over 6 times this cell. Once again we have to fix the h1 multiplying k1 plus 2 times k2 plus 2 times k3 plus k4, close parentheses, enter, and we have the same numbers as before, which is good. Right, so the rest is easy. We just copied out the formula. Right. Now, the step is 0.2, so the next x is going to be equal to this one plus the step sign. Again, we're going to fix that. And we'll just go ahead and copy this formula down. Where do we start? At 2, because the question asks us for the values of y of 2. Right, now, in this calculation, the y values is equal to the old y, so I'm going to copy that here. Right. And then all the formula here, I can just copy it down. And then the whole thing here, I can just copy it down. Right. That's it. And now let me show those are the values we have. Now if we want to plot it, just highlight this. Sorry, highlight the columns. I just want to copy that over here, so I don't want to mess with the calculation. Now I'm going to highlight that, and I'm going to go to insert and the graph and choose this one. It's going to be the scatter plot. Select the first one, and that is what we have. So exponential function, kind of close to what we have, right? Now, even better, let's do this. Put the chalk away. I'm actually enter the solution here. A second. That much better. Okay. Now the solution, actual solution we have from the previous page. I'm going to enter this solution in the calculator. This equal to that, sorry, not that, negative 0.5 times that minus 0.25, yes, plus 0.25 times E is exponential, exp 2 times that, and then just go here, double click, we have the values, and there's something wrong in the function. Let me check again. Oh, this is 0.5. and that's what we have. And then we can plot both of them. I hope it graphs the way I want to. This is right. And then you said, what happened to the first function? Why it only graphed the second one? Because if you won't see it, the reason being because the values are almost identical. So that's why the actual solution is on the top of the estimate solution. So this shows that we have the perfect solution. I mean, perfect estimation. So this method, that's why this method, even though that's a lot of work when we set it up, but if you see the solution, you can just see the numbers. This is the estimate. This is the actual solution. It is a very good approximation to the solution. Even though that takes a lot of work, if we have to do this by hand, it is a lot of work. But in the Excel, it's not that bad. And in here we can get the solution, which is very, very good already. Yeah. Compared to the solution we get from the calculator. When we use the improved Euler method, and this we use 20 steps. The answer is 25.429, which is a little off from this actual solution. This is the actual solution. The 25.4 is a little off. So the improved Euler method is not as good as this, obviously, because this takes a lot of work. So the results should be very good. So you see that with the step size 0.2, and when we do this, we almost get the very good answer compared to the actual solution and the approximate of the solution. So those two are very good. So, like I said, I will not put any of this on the test because it takes a lot of time, to type all of this in, and just want to focus on more important things. And the test is limited, so I cannot lose one page. So the test is limited, so I'm not gonna ask you to do any programming here, but it's nice to have. Of course, like I said, you probably don't have to program anything in the TI calculator, but the language is very simple, so that's why I use that. But the Excel one, though, it is very useful. Sometimes when you have to do, like, if we have to fix a shell, then you put a $sign in. So this is some nice tools that you might find it useful later, but maybe not now. But when you go to computer programming or electrical engineering or some kind of that require programming, you might appreciate what we do in here when we just do a few simple calculations and then we approximate the solution pretty well. Yeah, you might appreciate this later. But for now, I'm going to stop the video here. As mentioned before, I will not post any problem in these two sections on the test, but I still think that you will find helpful later. As always, thank you for watching. See you in another video in differential equation.